talk about understanding probabilistic topic models by simulation, which is very useful in text analysis. Without further ado, turn it over to Tim.
I am relieved to find out my skepticism is still healthy, so I'll continue to check in with Melinda on that. I think every time I've given a talk, I've apologized for my absence at RTA meetings, and I'm pretty sure the last time I was at one was the last time I talked, which was 1.5 years ago, which I'm very embarrassed of, but I'm not going to apologize anymore because it's obviously meaningless. I really appreciate this group, and I'm glad it's around, so I appreciate Melinda and the honorable board for making it happen, and John and Chris, everyone who helps make this happen. I really do appreciate it. And I just need to say to Brian Shepard, who's not here and asked if there's going to be a video, that's shameful that you're not here, Brian. He's at his daughter's second grade reading club or something, which that's embarrassing. I work at Distill Networks, which is we block malicious web bots for large websites. So we filter out automated malicious traffic from incoming web requests. We have an office in Raleigh and in 4 other cities. We are actually currently hiring, not on our data science team, which is what I'm on, but on our data engineering team. If anyone has experience with Java development and HDFS, Impala, streaming data, if you're interested in talking to me, I can get you in touch with those people. We have an HDFS cluster that grows by something like 10,000 records a second. So it's big data, which is actually not sexy, it's terrible. But I'm looking for people to come. That's not my team, but my job every day relies on that system working well. So if anyone's interested in that, talk to me. We're in downtown Raleigh. We're also remote friendly, but I think they're looking for someone who will be in downtown Raleigh for that position. And we have a beautiful new office. I have somehow there's a delay between things that I work on and how I ended up presenting them here. My previous job, I was actually I was developing a Python library for topic modeling, and I'm not actually doing this now, and I've left that job a year ago now. So I have been reminding myself about probabilistic topic models the past few days. And it's a really fun subject, and I hope it's interesting to you. The slides are an IPython notebook, and you can get them bit.ly/LDA-talk if you want. It's not the slides, but the notebook. Does anyone have no idea what probabilistic topic model means? It's totally fine if you do, but or if you do. OK. What is a topic model? A topic model, the concept of a topic model is trying to extract topics from textual data. And so it's not topic in any technical sense necessarily, but just given a bunch of documents, how do you know kind of what topics they're about? So you often see this if there's some sort of data dump, like with the Hillary Clinton's emails or the WikiLeaks or various things like that. People want to run that through some sort of automated system and say, kind of in summary, what are the topics discussed here? Probabilistic topic models are an approach for doing that, and that's what we're going to talk about. A particular type of probabilistic topic model called Latent Dirichlet Allocation, which is an intimidating name, but don't let it scare you away. Does that general idea of a topic model then, anybody have a question about that? That's a very vague thing, and now we're going to shift to talk about LDA, which is takes a very specific interpretation of that. So I just said not to be scared away by the name Latent Dirichlet Allocation, but the whole premise of this talk is that a lot of the resources out there are actually quite scary. And they scared me for a long time, and I'm here to tell you they don't necessarily need to scare you. So if you look on Wikipedia, at least last year, it said LDA is a 3-level hierarchical Bayesian model in which each item of a collection is modeled as a finite mixture over an underlying set of topics. Each topic is in turn modeled as a finite mixture, an infinite mixture over an underlying set of topic probabilities. Okay, so if that was helpful to you, you can actually excuse yourself because you already understand. If you've done some Bayesian modeling, maybe 3-level hierarchical Bayesian model actually might make a little bit of sense. But it's really not, that's not very clear, and I doubt reading the Wikipedia article is going to clarify it a whole lot. An alternative definition is this, W sub I given Z sub I, phi super Z sub I is distributed according to a discrete distribution with parameter phi Z super sub I. And so again, like if you're a statistician and you're used to reading statistical literature, maybe this is a helpful thing, and you could start to kind of think about what's going on here. I mean, what we're describing here is this hierarchical statistical model. But what's definitely not clear here is what this has to do with text documents, right? And how this even relates to text documents. So I don't think that's particularly helpful. It's not for me. Even worse, I think, are plate models for Bayesian networks. A plate model is a means of sort of summarizing a complex probability model. Yeah, I took a graduate level class at NC State in Bayesian networks, which is what this is, and for better or worse, I look at plate models and still they mean nothing to me. And if it means something to you, that's great. This is really not helpful to me either. So you could look at the likelihood function for latent Dirichlet allocation. I'm not going to read that for everyone's sake, but again, maybe if you know something about statistical modeling, you could start to pick apart what that means. But in any case, you have to sit and think really hard about what that means. It's a pretty complex thing going on there. We've got products and sums and integrals. Here are 4 different ways that you could define what latent Dirichlet allocation is. And I think for most people, even, probably most people in this room have technical backgrounds. I suspect none of those are really going to be all that enlightening. So the premise of this talk is going to be to try to illustrate what is going on with latent Dirichlet allocation through Python code and through working through an example. And something that I don't have emphasized well enough in these slides is often when you, or arguably maybe always, when you think about statistics from a Bayesian perspective, when you define the mathematical model that you're trying to fit to your data, you're actually defining sort of the way your data itself is generated. So you've heard the term generative model. Instead of just simply finding kind of a means to an end of solving your problem, you're actually describing what your data looks like. And so when we think of latent Dirichlet allocation, which again, you still don't really know what that means, instead of thinking of a way to take a bunch of documents and extract some topics from the documents, instead what we're going to look at here is how do you generate documents according to a mathematical framework. So ignoring any real world data for a moment, say we sat down and said, hey, I want to use random number generators to construct documents. How would we do that? And it turns out that's what latent Dirichlet allocation is completely premised on. And really, when you solve the statistical problem, what you're doing is saying, given that I'm generating documents, and given that I have some documents, what parameters are the most likely parameters that generated those documents? And so you're solving your model to find those parameters, and then what you're saying is, I think these documents were generated by this mathematical model using statistical sampling. And if that already makes you say, well, I know a lot about math, and I know a lot about the English language, or maybe another language, and it seems unlikely to me that you could actually generate meaningful English sentences using math, you're already on your way towards realizing that there are serious limitations to doing this, to looking at data or looking at documents in this kind of a way. Because that's really what we're trying to do, and that's a simplifying assumption we're making. So keep that in mind as we go forward. Any questions? This is now where we're going to kind of get into the meat of this. Any questions at this point? All right, so I'm sorry about the labels on these graphs. They're probably hard to read for anyone very far away from these. But this is just a histogram of the sepal length of 2 of the irises from the Fisher iris data. Probably most people are familiar with Fisher iris data. We're just plotting a histogram on a graph. So a question we could ask is, given that we know this is data that comes from 2 different types of flowers, could we try to discriminate the data to divide it between the 2 classes, or between the 2 sources, the different kinds of flowers? And so we're making the assumption that we know that this comes from 2 different types of flowers, which is an interesting assumption on its own, but just starting from that point. And so if we wanted to do this in an unsupervised way, if we didn't actually have the labels, the most obvious thing we would do is just jump in here and say, well, I'm going to divide this between what appear to be 2 modes of this graph. And maybe it has 3 modes, but 2 really obvious modes. And so I'm just going to divide the histogram by those modes. Right, so we could just slice it right like that. And if you've taken, even a data mining class, or probably even a lot of introductory statistical classes, you know that this is something like linear discriminant analysis, which has the same abbreviation as latent Dirichlet allocation, even though they're completely unrelated. But that has caused confusion for people at times. So in linear discriminant analysis, what we're going to do, well, I'm going to take one step back for just a moment before we think about that. Put linear discriminant analysis out of your head for a second, and imagine that we separated these into 2 groups just by eyeballing it, and then put a dividing line down the middle. If I then asked you, so you have this model for your data of how you divide it between the 2 groups, can you then generate me more samples that look like the data we have? With what we have so far, really all you could do is put a random number on one side of the line or on the other side of the line. But you don't have there's no sort of framework here for generating data. So what I'm trying to illustrate here is when we often use the words, talk about generative or discriminative models. Here we're not talking about a mathematical model that in any sense models how the data is generated. We're just discriminating between the groups of data. But if we move forward to linear discriminant analysis, often what we're going to do is say, well, let's assume each group of our data is Gaussian distributed, and then find the 2 Gaussian distributions that most make sense for this data. So here's what the real underlying data looks like. This is straight from the Fisher's data. You could download it and make the same histogram yourself. The blue is one type of iris, and the green is another type of iris. And so if you look at that, and if you squint enough, you could say, I could imagine that those are actually Gaussian distributions. They don't look like a perfect bell curve, but there's something like a normal distribution going on there. So we could define then a mathematical model where we sample data from Gaussian distributions, and they have different parameters, and this gives us these two different groups. And so then the question we could ask is, if we assume that this is a Gaussian distribution and this is a Gaussian distribution, what are the most likely, we might say, most likely parameters that generated this data? And in linear discriminant analysis, what we're going to do is try and answer that same question when we don't know the two colors here. So imagine we're back to our previous graph, and we say we think this is made up of a mixture of Gaussian distributions. These are numbers generated from two different Gaussian distributions or normal distributions. What are the most likely parameters for those distributions? All right, so the reason I'm kind of hammering that hard is because that's the exact same framework that we're going to think about when we think of latent Dirichlet allocation. I originally gave this talk at PyData in New York City. So all the code which is going to be a lot of the slides following, is Python code. It all makes sense to me. I look at Python every day. If there are things that you have questions about, feel free to ask, but most of it is going to be pretty readable. So let's try and see what that would look like to generate data from this model that I'm describing. So we're going to define mixture proportions. So what that's saying is that we're going to assume the two groups are about the same size. So the proportions are 50-50. And then our means of our Gaussian distributions are going to be about 5 and about 6.6. So I just guessed from here maybe about 5 and here about 6.6. And then I gave it standard deviations for the two distributions. So I'm defining all these parameters for a model, and what I'm saying right now is that those parameters are going to generate data that looks similar to this. So I have 100 data points. For each data point, I'm going to go in and randomly choose one of my iris types. So I'm just going to say, am I A or B, given a 50-50 division. And then I'm going to generate the sepal length from these mean and standard deviation for one normal distribution and mean and standard deviation for the other. And which one I choose depends on which iris type I generated in the first line. So this is just saying generate a random normal variate, and then I'm going to append it to a list. So if I do that, I generated data randomly that looks like this. And if you remember back to the graph we just had, it looks something sort of maybe like that data that we just had. Right? Any questions right at that point then, how we came up with this? All right, so so far we're manually specifying all the parameters for our model. If we want to take that a step further, instead of just manually specifying all these parameters, we could also, these are just numbers, we could get them from a probability distribution. So we could define probability distributions that generate all these numbers just for fun if we want to. We're going to generate our mixture proportions from something called Dirichlet distribution. The name probably rings a bell, and I'll talk about that more in a second. And then our means, we're going to assume that these also come from a normal distribution, so the means of a normal distribution from a normal distribution. And our standard deviations we're going to draw from a normal distribution just because it's easy. So just a brief aside, what is a Dirichlet distribution? It's a continuous distribution over unit vectors. A sample from a Dirichlet distribution, so it's a probability distribution. If we draw a sample from it, could often be itself considered a probability distribution. And that's a little bit confusing. We're thinking about a distribution where a sample is itself a probability distribution. In our example problem, a sample from a Dirichlet distribution determines the relative number of data points that go into each of our groups. So by sampling from unit vectors, we mean that if we draw a sample, it's going to add up to 1. And in this case, we have just two elements. All a Dirichlet distribution is like random sample that generates a weight saying how likely our coin is to be heads or tails. Put another way, we're talking about 2-dimensional Dirichlet distribution. You could also think about it 3-dimensional and draw 10 random variables from it. So each sample from our distribution, if you look at these numbers and you add them up, they're going to add up across to 1. So this is a sample from the distribution. This is a sample from the distribution. And all of you could consider this then to be a probability distribution where you have like a 3-sided die that you're rolling. And it's the likelihood of it landing on each side. If that is a little bit confusing to you, if that's the first time you've ever heard that, hopefully that's a helpful start of an introduction. But you're going to be able to follow, I think, the talk without understanding that. So this is maybe thinking about our model in a slightly more Bayesian fashion. So we want to generate data that looks like this iris data. So we're going to randomly choose our mixture proportion from a Dirichlet distribution. We're going to randomly choose mean, and we'll randomly choose standard deviation. And then we're going to sample 100 data points. And we're going to sample exactly the same way we did before, except instead of using our fixed parameters, we have these randomly generated parameters. And so if we run that, we get, again, data that looks like this. Now, it might be shifted or skewed a little bit differently from our earlier data. But you see that this looks something similar to the data that we had originally. But this is data that we just randomly simulated using Python. The code here is just making the plot, so you can ignore the code. Right? So we randomly generated this data. If we ran all the same code again, we would get different looking data. So here's just the same code. We could run it a second time, and we get completely different looking data. But we see, again, it's these 2 Gaussian distributions. OK, so all we're doing right now is randomly generating data. And what you're saying to me, maybe, or thinking, is how then is this connected to machine learning or to Bayesian modeling or these various things? And the idea, and this is a big idea in this whole talk, is that here we're thinking about generating data in a forward fashion. We could instead start from our data and work back up, and what work back up means is a little bit irrelevant right now, and say, given this data, what are the parameters that were most likely to have generated this data? So we could go back to our iris data, our histogram that has 2 modes, but we didn't know which group it's in, and say, we're going to assume that this came from 2 different normal distributions. What are the parameters that were most likely to have generated that data? And most likely could mean different things. I mean, if you've heard of maximum likelihood estimation, for example, that's a way of defining what we mean by most likely. Or in a Bayesian context, we're going to start with what we're going to call our prior distribution and say, like, well, we have some idea of what those parameters must have looked like. So let's start with those and then feed our data into it and then get this Bayesian estimate, which instead of just being a single value like you get in maximum likelihood estimation, you get a distribution. But all those things are important, but a little bit irrelevant. And the idea being, what we're trying to do is have some data, define the process that we think generated that data, and then work backwards on that process and say, what are the parameters of that process that made this data happen? So in our example here, given data without cluster assignments and in no particular order, first we need to specify which cluster we think the point is most likely to come from. And then for each of our two clusters, what are the parameters that, if they're normal, what is the mean and standard deviation that define that cluster? And then somewhat related here, what's the mixture of proportions between the two clusters? So what are the relative sizes of the two clusters? So instead of working forward to generate our data, we're working backwards to find our parameters given our data. Yes? Yep.
When you say find the parameters of each cluster, you talked about a Bayesian approach. Is it repeated simulation to find the optimal set of parameters, or is there an algorithmic way to determine the parameters?
Yeah, so that's a very good question. So the question is, when we talk about finding the parameters, do you just like run some algorithm to find those, or is there an optimal way to find those? The answer to that question depends on being more specific about what you define, how you define the problem. One possibility is that you could take this and you could take your likelihood function, which we talked about the likelihood for latent Dirichlet allocation way back, and you can frame this completely as an optimization problem, and you can just solve that and get that's like a maximum likelihood or a map estimate, MLE or map estimate. So that's one option. In a Bayesian context, what you often end up doing is instead of thinking about trying to find fixed values for your parameters or point estimates, you're instead going to say, let me describe these as probability distributions, which we kind of did in sampling, and find what were the most likely probability distributions, which in some ways helps capture uncertainty that we have because of noise or other things. And when you do that, you can also frame that as an optimization problem. My background's in operations research, though I'm pleased to find out everything is actually just an optimization problem. But another possibility is if you hear about MCMC, Markov chain Monte Carlo, arguably also sort of an optimization thing, but essentially what you're doing there is figuring out a way to draw samples from these probability distributions that we're modeling. And so then you run this thing for a long time, and it's painfully slow, and it just spits out random numbers, and those random numbers you get to interpret as the distributions describing the parameters of your model. Does that help? And so if you want to apply this stuff, you have to start to understand those things at a little bit deeper level. In this talk, I am not hoping to tell you at all how to actually solve latent Dirichlet allocation and actually find topics in a model. What I'm hoping to communicate is how the model actually works, which is a big step. Is going to really help you as you try to solve it and try to interpret solutions. If you want to do this thing that I just described here, in Python there's a library called PyMC3. There's a notebook called Gaussian mixture models in PyMC3, and this will tell you exactly how to fit a Gaussian mixture model, which is what we're just describing, to data. So this data looks kind of like ours, and it's going to run all these Markov chains, which give you a bunch of random numbers, and it's going to turn out you can interpret all those random numbers as describing the parameters of your model. And it's quite magical and fun if you have the patience to let it run. Anyone who has spent time doing that, I'm sure knows what I mean. Unfortunately, I navigated out of my slides, which is bad news. Oh, good. I also have an IPython notebook. Just one second, I will field that question. If you're interested in math, which is my favorite, I have an IPython notebook that you can look at that talks about how you derive the math to actually do this. And so to give you an idea of what you're missing out on, you get things like this. But my contribution here is that I do the math and then I actually write it all out in Python. And so you can work through both. But it's quite a blast to do this stuff. I think so. Melinda also thinks so, I bet. The question?
If I have two Gaussian relations that potentially overlap, there's no way I can assign a particular point to one or the other, but I don't need to do that in order to recover the parameters.
Yeah, I mean, so if your data doesn't, if you don't have enough data, so the question was, what if your Gaussians overlap? The short answer is you just don't have enough data in that case. You need other dimensions to your problem or something to figure out how to do that kind of discrimination.
I don't need to assign, I can't assign a particular point to one or the other, but I don't need to in order to abstract the parameters of the model.
Well, you would, yeah. I mean, it's not magic, right? So if there's no way to tell the things apart, just because you do a lot of fancy math, you're not going to be able to tell them apart. Does that?
Rule of thumb, they need to be, sorry, I'm totally interrupting, I'm sorry. It needs to be at least one standard deviation apart, right? That you need about one standard deviation to separate them.
I'm just saying that your first step here, find the cluster for each
Right.
might not be necessary in order to find the parameters.
But you can't start talking about, I mean, for the recording, the question is, what if you can't tell your groups apart? Can you still find the parameters? But I mean, and one way you can think about it is, if you can't really discriminate, there are potentially like infinite possible ways to discriminate. And so I don't actually know exactly what happens if you try and fit something like that with MCMC. But typically, mathematically, if you have this optimization and you're looking for infinite number, or there are an infinite number of possible solutions, it's never going to converge on your solution, or various things could go wrong like that. But the reality is a one-dimensional Gaussian discriminant analysis is only interesting in textbooks. I mean, if anyone has a counterexample to that, I'd be curious. But you start to define models where you have much more complex data, that's where it really gets to be interesting. But I mean, I don't know about how all this necessarily happens, but often if you try and define models for this kind of thing, you end up having like matrices that are ill-conditioned, and then you have numerical instability as you try to solve, like all kinds of disastrous things try to go wrong if you have an ill-defined model like that often. All right. So to move one step beyond that, just to get Melinda's comment a second ago on the recording, what Melinda said is a rule of thumb is you want your groups in a Gaussian distribution to be a standard deviation apart before you try and fit them. But that was not related to this slide, but I just thought of that. So I say there's nothing inherently special about a normal distribution, which is supposed to make everyone in statistics training laugh. Because we know that there's everything special about normal distribution, maybe the specialist of distributions. But in this thing that we're doing, as we were generating data, we were like sampling from a normal distribution. But in our Python code, it's clear we could just throw any distribution in there we want. So we could define our mixture proportion again, and then we could define these cluster distributions, which are just numbers that happen to sum to 1. And then for every data point, we could randomly choose which cluster the data point is going to be in. And then instead of drawing from a normal distribution like we did a second ago, we could just randomly choose between snake, panda, and bar chart. So anyone who's knowledgeable about Python knows that this is Python 3, because we have beautiful Unicode like right in there, and there are no errors anywhere, which is great. And so we could randomly choose from snake, panda, and bar chart using, if we're in cluster 1, a 30% chance we get snake, 30% chance we get panda, 30% chance we get bar chart. If we're in cluster 2, 20% chance we get snake, 80% chance we get panda, and no chance we get bar chart. We can generate data like that. There's no one stopping us from doing that, right? So then we could get these two groups of data, which we can't plot in the same way, but we have a bunch of snakes, a bunch of pandas, a bunch of bar charts. And the top one and the bottom is the same, except no bar charts. And we can see this one is about roughly twice as big as this one, give or take a little bit. All right, so we can start to describe how we generate data any way we want to. And this is the great promise of Bayesian statistics, is that if you can describe how you get your data, then you can fit this beautiful statistical model to it. The big real world question of that is can you actually fit the model to your data? And the answer is often not just for anything you can describe, but people like to make that claim anyway. So we can extend this again, and this is all kind of hypothetical at the moment, but what we're going to see is that this is going to work up towards our mathematical description of generating documents. So instead of defining our mixture proportions and defining our cluster distributions, we could sample our mixture proportions. So that's whether or not you're in group 1 or group 2 from a Dirichlet distribution. And then for each group, we have a cluster distribution defining how likely are you to have snake, panda, or bar chart. And so then we could just randomly generate those, then randomly select each of our 100 data points. And we have no idea what we'll get, but we can look at our output. And we have something that looks a little bit similar to what we had before. But all of this is randomly, this is like a random sample. You could consider all of this as like a complex probability distribution, and this is a random sample from it. Cluster 1 and cluster 2. But instead of normal random variates, we have just these crazy discrete things described by Unicode. Why do we do that? We're moving closer and closer towards describing creation of documents. Right? So right now, as we generated a data point, we just randomly chose which group it's in and then chose which word or emoji we want to generate. What if we stepped it up a little bit and said, we have a vocabulary again, and then we have boring vocabulary to play nice with matplotlib. But what if we also had two different topics, one topic called sunshine and one called clouds, and then sunny and cloud here. And what if the way that our words are distributed within the topics are defined by some sort of probability distribution? So what we're saying here is in the sunny topic, it's 10% chance of being a snake, 30% chance of being a panda, and 60% chance of being a bar chart. Sunny days and bar charts go together. And in the cloud topic, it's an 80% chance that we get a snake, a 10% chance we get a panda, and a 10% chance we get a bar chart. And then what we're going to say down here is a sunny topic is 30% chance, and a cloudy topic is a 70% chance. And so that's a lot to keep. Sorry, I keep whacking the mic, John. I really apologize. That's a lot to keep track of in your head. But so here we're saying the cloud topic is 70%, sunny topic is 30%. Within the cloud topic, snake is the most likely word that we see. And in the sunny topic, bar chart is the most likely word that we see. So then we could generate documents based on these parameters. Right? So what we're assuming here is that we know we have 10 documents. And what I'm going to do as I generate each document is randomly choose a topic the document's going to be about, and then randomly choose the words from that topic. So I want to generate document 1. I randomly choose its topic from this discrete distribution. Well, 30% chance I got sunny. And then in this case, I'm going to randomly choose how long my document is from a Poisson distribution. That's fine. I mean, you could generate how long it is however you want. And then I'm going to generate all my words or my emoji in my document from the word distribution that corresponds to the topic. So remember, sunny topic is most likely to be about bar charts. So this document that's about the sunny topic is mostly bar charts. And then another document that's the sunny topic, it's mostly about bar charts. A cloudy document, mostly about snakes. Again, cloudy about snakes, cloudy about snakes. And then we're back to we got our sunny document, it's about bar charts again, right? And then clouds, it's about snakes. So this is a crazy thing, and it's the kind of thing when I learned how to program my TI-83 calculator in 7th grade, I would have just like made stuff like this all day long and thought it was the coolest thing. But in reality, like this is a completely useless thing, right? Other than making a cool picture, this doesn't help anyone. You don't want to take this and show it to your boss and say, I understand all the documents in our data now. I can randomly generate meaningless documents, right? And so also, why am I saying documents? You can look here, and these are emoji, but you could also think about these as being words. And you could think about making your vocabulary way bigger than 3. You could make it really large. You could even empirically construct topics by like loading in a bunch of documents and then just counting the words and using those relative or empirical distributions here. And so you could generate a bunch of words, right? And so you could call it a document. There's one glaring, maybe multiple, but what is a glaring issue with calling these documents? Any thoughts? It's the only class participant. What? There's no punctuation. What? There's also only one topic per document. All right, so there are at least 3 glaring issues. The third one being, I guess I'm talking about it in a second. The third one being that word order is completely arbitrary here. And you can see that by the fact that I actually just sorted these. So this isn't the order in which they're generated. I have sorted here. But in the way I'm talking about this, word order doesn't matter. So keep that in your mind for a second. I thought that was the next slide. But it's coming up in a moment. But the other things mentioned, punctuation and one topic per document is also relevant. But, all right, so thinking back to our Bayesian model in our example earlier, we could try and reverse this process. So we've defined a way for generating documents. We could start with a collection of documents and then find the topic of each document and find the distribution over topics. So what's the proportion, the likelihood that a given document is about a given topic? And then we could think about, within that topic, how are the words distributed? How likely is it, if your topic is sunshine, how likely is it you're talking about bar charts? Right? So in our heads, maybe we could imagine some sort of mathematical means of starting with documents and thinking about our model and then finding the parameters that we had in our model, right? So these are all our parameters for our model. We could try and figure out what they are. We're not going to do that, but it turns out you could actually do that if you wanted to. So there are several obvious limitations here in thinking about real-world data. One is there's a single topic per document. That's a huge limitation. If you know much about how documents get written in the English language or just in any situation. Another implicit assumption that I just said I'm making is that the word order is irrelevant. So this is what you call the bag of words assumption. A third thing we didn't talk about is this also is assuming that we know the number of topics that we're dealing with. So the first issue we're going to step forward and try to deal with. The second 2 issues are implicit in latent Dirichlet allocation, and they're massive simplifying assumptions about language that are in basic latent Dirichlet allocation, just something you have to deal with. And so I put in a slide here to try and make that hit home. Again, I gave this at the PyData conference, but For those who don't know, in Python you can type import this, and it's kind of an Easter egg. It prints out something called the Zen of Python, which I've concatenated all together here and stripped out the punctuation. But the Zen of Python is beautiful is better than ugly, explicit is better than implicit, simple is better than complex, complex is better than complicated, and so on. Right, so that's already without the punctuation, it's kind of weird. But if you make the bag of words assumption, you could probably go back in and figure out the punctuation here. But if you make the bag of words assumption, the Zen of Python is a, although, ambiguity, and, are, aren't, at, bad, b, beats, beautiful. If someone memorizes that, you could recite it at maybe Chris will let you recite it at PyData next year. Zen of Python in alphabetical order. But what I want you to look at this and say, well, that's an absurd thing. Like, how do you think about, you can't think about English language and say the word order doesn't matter. That's a huge lie, because people do that all the time when they do text analysis. And what I think looking at latent Dirichlet allocation in this framework that we're building up here helps you see is these kind of limitations. And hopefully this is the healthy kind of skepticism that Melinda said I have, in that latent Dirichlet allocation has been a very touted mathematical model. Like, oh, here's this impressive, complex Bayesian model developed by some of the hot shots of machine learning and Bayesian models, David Bly and I think Michael Jordan, and some of these big shots when they were at Berkeley or Columbia or wherever. And oh, it's so impressive, and the math is extremely complex, and computing it is difficult, and all this various stuff. But the reality is, underneath, it's making this really stupid assumption about how language actually works. To be fair, if you've ever tried to do any text analysis, you've also made really stupid assumptions about how language works. Because text is really, really complex, and language in particular is very complex. But
you would be less stupid, albeit more computationally intensive, by considering dyads, for example.
Right. So the comment was you could be less stupid by considering more complex ways of modeling things. With Bayesian models, you could be less stupid if you have exponentially more time to wait often, meaning very quickly, if you have 1 billion years, you could maybe fit your model to 100 documents. So the reality of that goes out the window pretty quickly with many solution methods. But even then, nothing is perfect because at some level language itself isn't perfect. All right, so we're going to take one more step up. I'm going to jump ahead. I'm sorry, I don't like when speakers do this, but I'm going to do this. We're going to change one thing we were doing in our previous model, and that is instead of assuming each document is about a single topic, we're going to generate our document as a combination of multiple topics. So what we're describing here in this Python code is a process of generating documents by generating them one word at a time. And the way we're going to generate a word is we're going to say, I want a word. Python, I want a word. And what it's going to say is, OK, I'm going to flip a coin, decide which document you're in. And then I'm going to flip a coin specific to that document and decide which topic you're in. And then I'm going to flip a coin specific to that topic and decide which word you are. And that is what I just described to you, and what we have here in Python is a generative model that we call latent Dirichlet allocation. All right. So I'm assuming I have 10 documents. It's a hard-coded parameter. I'm going to something I didn't just mention is I'm going to randomly select the length of the document, the number of words in the document from a Poisson distribution. You can do that or not. In reality, when you're fitting these models, you know how long your documents are, I hope. Right, so I'm going to choose how long my document is, and then I'm going to choose a probability distribution called mixture proportion that determines how likely I am to be in one of two topics. So I'm knowing I have two topics. So now I want to generate all the words in this document. So I'm going to say randomly choose one of the topics based on the mixture proportion. Sorry, I should have clarified this to start. This mixture proportion is inside the for loop that corresponds to this document. So this mixture proportion here is specific to this document. So what I'm saying is the way my two topics are distributed within this document is specific to the document itself. So if you think our sunny and cloudy topics, in this document, maybe the distribution is 10% sunny and 90% cloudy. In another document, it might be 50-50. Right? So I'm going to generate words given that document-specific proportion. And then once I've decided on my topic for the word, I'm going to randomly choose my word from the vocabulary using the word distribution. And in this case, the word distribution is specific to my topic. I think I might have accidentally deleted a slide out of here that set some of this up. I'm sorry about that, but we'll just roll with that. But we chose our topic specific to the document, and then that topic also has an associated distribution of words. So that's how likely snake panda bar chart is within that topic. Actually, you know what I did? This is recycling my distributions from the previous example. That's where that came from. And so I'm randomly choosing the word from that, and then I'm just inserting it into my document. Right? So that was a confusing explanation and some Python code, but I think where this gets helpful is when you get to see the output. So what did I do? I generated 10 documents, and each document is composed of words generated from one of two topics. But the vocabulary of the topics is shared, or the vocabulary is shared between the topics. It's just how the relative frequency of the words within the topic are different. Right? So sunny and cloudy are both about pandas, snakes, and bar charts. It's just that sunny is more likely to be about bar charts, and cloudy is more likely to be about snakes. So document 1 is mostly from topic sunny. It's a lot of bar chart talk. Document 2 is all from topic sunny. Document 3 is mostly from document sunny. So on. Down to document 6, it's mostly from topic cloudy, and cloudy is mostly about snakes. So I did something here. Again, we've already talked about I sorted these things so that the characters all occur together just because it's easier to see the random frequencies. And I also divided the words based on whether or not they're from one of the two topics. And I also used emoji instead of words. And I also used a very limited vocabulary, 3 emoji or 3 words. But that's also to illustrate a point that latent Dirichlet allocation, which we're describing, this is how latent Dirichlet allocation is assuming your document is generated, is a process exactly like this. And it's assuming that the order is completely irrelevant. And so the way that you order it in an example like this, it doesn't matter, right? So the latent Dirichlet allocation knows nothing about the ordering of your words. Hopefully that is hitting home. But there is a slightly subtle thing that's going on that is very interesting. And going back, I said that the two the vocabulary between the topics is shared, right? Both topics are about snakes, pandas, and bar charts. And what that means is if you fit latent Dirichlet allocation to your documents, in theory, it can start to detect that the same word spelled the same way might be used in different senses, right? And what that means in concrete terms is you run latent Dirichlet allocation, and it might, when you run it, it assigns a topic to every word, right? So it's saying, here are your documents, and here are the topics I think each word is in. And if you use the same word multiple times, it might get assigned to different topics, right? And so I'm kind of emphasizing the simplicity of the model in that word order doesn't matter, but it actually does have these more nuanced things where it can potentially detect that a word can be used in multiple different ways. And this is an extreme example, but it's just a little bit funny. Hopefully people know there's a grammatically correct sentence: buffalo, 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 buffalo. This is from the Wikipedia page, the sentence diagram, and you can look it up and see what it means. But the reason I use this is it's one word repeated over and over. Latent Dirichlet allocation would probably fail miserably in this particular example, but it does have the power to detect the nuances of how words get used in different ways. All right, so same thing we've talked about over and over. We just described how to generate documents using this random probability model where we fixed our parameters or drew our parameters from random distributions. When we do the whole latent Dirichlet allocation process, what we're going to do is take a collection of documents, right? So we know, you can think of a collection of documents as like a ragged array that has like word counts, right? So document 1 is just you use the word and 1,000 times, the word the 500 times, whatever words. So we know how long the documents are and exactly what words they're in. And we also know exactly how many documents we have, right? So those are not uncertain things. Those are known things. So for each word in each document, we want to find the topic that word came from, right? So we have some number of topics. We want to assign to the word the topic it came from. We also want to know for each document, how are the topics distributed within that document, right? So given this document or given this Hillary Clinton email, how likely is that email to be about weekend plans versus a situation in another country or something like that? Finally, we want to know, for a given topic, how is the vocabulary or how are the words distributed within that topic? Right? So all of these things are things that we kind of defined as we generated our documents previously. Instead, we want to start with some documents and then figure out what are those numbers that characterize each of those probability distributions. Yeah, so that's the distribution of terms is just the distribution of the vocabulary. So given your topic, it's like a large categorical distribution over your vocabulary. Which word are you likely to generate? So that is the grand and exciting conclusion of this talk. The plus or minus a few more slides. If you want to do this, you have to do something completely different from anything I've described here, other than briefly earlier. You have to do very complex mathematical computations to actually do this. Right? So this is the blessing and curse of these Bayesian type models. They're often or potentially very easy to describe, but very complex, possibly, actually solve. So you might have heard of MCMC. I know some of you are well acquainted with that. For example, Gibbs sampling or other types of samplers, Metropolis sampler. Something called variational inference, which are approximation-based algorithms. So you're going to turn this into an optimization problem and then solve a simpler version of the approximation, the optimization problem, or otherwise. There are other things you could do. Which I'm happy to talk to you about if you have more questions about that. So in this model, we eliminated the concern that there's a single topic per document. There are a number of other limitations. As we've already mentioned, some important ones. Word order is irrelevant. We're considering the bag of words model. Hannah Wallach, who is a very well-known machine learning researcher, I think her dissertation was on this topic, no pun intended, or at least some of her significant contributions. As far as I know, her ideas for dealing with the word order issue haven't been implemented in good solvers, which is too bad. We're also assuming here that we know the number of topics, and I haven't really hammered on that hard enough, but this is assuming you have a whole bunch of documents, and maybe you have thousands of documents, and you go to solve this with some computer program, and you go through your command prompt, and it's going to say, well, how many topics do you have? And you're going to be like, I have no idea. I want you to tell me that. That's the whole point of using it. But in latent Dirichlet allocation, you have to specify the number of topics. And as with other things like k-means or something, maybe you solve it with multiple numbers, and you somehow decide which one's the best fit. You can also use something called hierarchical Dirichlet process models. This is what I was working on in my last job, actually. The math and computational complexity just explode as soon as you do this. But this essentially allows you to make the number of topics also a parameter of the model by using these infinite dimensional prior distributions. And it's very interesting. And I have a Python-based implementation of a Gibbs sampler for this. So if you're extremely patient, you could actually do that. And I'd be happy to talk to you about that. But those are both real limitations. And there are other real limitations. Melinda mentioned punctuation. And there are other things. We're assuming that each word comes from a single topic. Maybe we could use language more complex than that. So I'm showing you this for two different reasons. This is from a very good paper, if I remember correctly, which one this is from, on latent Dirichlet allocation. And this is trying to illustrate this generative process. So what it's showing here is that a document is a distribution of topics. And then each word, this is like each circle here is corresponding to a word. And the color is showing the topic of the word. And then we're generating the word from each topic. So you can see here, this is like the hierarchical framework of the Bayesian model. And so I think this is maybe a little bit interesting. As you can see, like this is illustrating what I was illustrating with Python, which is here's this hierarchical process where you can generate a document. And what we want to do is then reverse that process and then maybe fit numbers to these probability distributions. Where I think this is misleading and why I have this talking about bag of words assumptions is, my opinion is things like this are confusing in that this indicates that the word order matters. But latent Dirichlet allocation doesn't know anything about these word orders, so this isn't really how a document's generated, because it's just generating a bunch of words, and someone very cleverly put them in the right order here. So I'm hammering hard on that, but my more meta point there is like you really have to evaluate the assumptions that you're making with these kind of models. And I don't want to be the one to keep people out of applying predictive analytics and machine learning and various things, but this is the risk. If you're new to this, or people on your team are new to this, you go and apply some very nice library. I think you can do variational inference, which is very fast. with LDA using scikit-learn for those who are Python programmers. And I am a full supporter of that kind of thing, but sometimes the limitations of your model are subtle and hard to understand. And it really, not an encouragement to keep you out, but an encouragement to keep studying and keep trying to understand the things that you're doing with your models. To point you to a few resources, and then if there's time, I'll be happy to answer questions. I think a lot of the literature on this stuff is really terrible, to be frank. Even the technical literature in good journals is sometimes very bad, and I think that's unfortunate. I won't say more than that, but David Bly, who is one of the original developers of this stuff, he has a very good paper, or it's like a more friendly introduction to topic models that was in the Communications of the ACM. If you're interested in this stuff, I highly recommend going out and reading this. And I wouldn't say that for all of David Bly's stuff. Despite he's obviously very talented, but it's just not always that clear. And I think you can be lost in a lot of the math and a lot of the hand waving. But this is a really good piece, so I highly recommend that. This is a blog post by Edwin Chen, which is a similar approach to this from my own presentation, and he was inspirational to me in this in some ways. It's a friendly introduction to how this works. I recommend that to you. There's a good, for Python programmers, this is the package I recommend is called LDA by Alan Riddle, who's an academic, but it's a Gibbs sampler for LDA. For various reasons, I'm partial to Gibbs sampling over approximation methods like variation methods, which is probably not a fair bias, but it's a very usable package, and I found it more approachable than what people often recommend, which is the GenSim library. If you're interested in the math, I have some resources I'd be happy to point you to. One I linked to earlier, but the Finding Scientific Topics by Griffiths and Stavers. And then this is really cool, is if you're doing this kind of stuff, PyLDA Viz by Ben Mabey. Let's see. Here's a way of visualizing topic models using Python and this interactive JavaScript little thing. This is like movie reviews or something that he has found 20 topics and then used multidimensional scaling to plot it on 2 axes. So these are your topics, and then you can like hover over each topic, and it shows how the words are distributed within that topic versus like their global distribution. So you can see, and something I should have done sooner is explain that in LDA what we actually mean by topic. I never really defined that to you, but what LDA means by topic is the distributions of words, right? So it's extracting words from your own documents in an organic fashion. So you're not specifying the words, but you're kind of determining your documents by extracting the topics from your document. So here's this very common topic. It's big. It's about films, movies, time, the word good, character. Character is character, film, and then you have more obscure topics that might be something like files, Ryan, movie, Tom, series, Hanks, sixth, Oscar. Let's see if that one's mostly about sex. So this topic is Scream, horror, killer, Smith, summer. So slasher, maybe those are about horror movies, also horror movies. Action, Jackie Chan, fight, Hong, Van, Kong, Chinese. So you could guess what that topic is about. Disney, animated, animation, wars, story, start, right? So you can, this is just a really helpful tool to start to interpret these things, because what these models do is just dump a bunch of data back to you, and you have to start to make sense of it. This is a really nice way to do that. All right, so I'll stop talking, and I'd be happy to field questions. Sorry, I meant an hour and 15 minutes, Chris, not an hour. I'm kidding. But I don't know when we have to leave, but I'm happy to answer any questions.
So as